Good morning. I'm going to take a little bit of a different tack with this talk. My name's Arjun Hassard. I'm head of product at NewCipher. NewCipher is a decentralized access control layer, which I will explain. I'm going to talk about a fairly esoteric topic, which is the protocol design for staking networks. By staking, I mean that collateral is a primary mechanism in the network, or the presence of collateral. I have two objectives for this talk. One is that I provide something of a shallow ramp into this, so no equations, it's pretty straightforward. Some ugly diagrams there. And the second is that I can present a few open research problems, and then also some solutions and partial solutions, so that we end on an optimistic note. So resource network. By resource, I mean some kind of infrastructural service that would be essential to like a Web3 stack. So access control is one, that's what NewCipher focuses on. But also you could have like indexing on demand or outsourced computation or something where there's a network involved that's doing some service for you. Access control is also a little bit of a narrow service, but it's actually essential for things that are present in every single major application, like data sharing, key management, messaging, things like that. The basic dichotomy that we kind of present when we talk about our product is, do you want your permission management or your access control enforced by some third parties, like a key management system or a data custodian or the developer of the app? Or do you want it enforced by cryptography? In our case, the breakthrough that we work with is threshold proxy encryption, and then decentralization paradigms, which is what I'll focus on in this talk. So things like distributed computing, how does one node learn about another one, and also, of course, the economic layer. Before I get to that, I think it's really important I establish what the service that we offer is. And the really important question that comes to mind when developers are thinking about integrating NewCipher is, why can't I just use like TLS or some public key infrastructure? Let's go through a quick flow, sort of generic one. So data owner wants to share data with some designated recipient. The first thing they do is decrypt it into plain text or decrypt a SIM key associated with it. And then they can encrypt it again using the public key of the recipient for Bob, and then again for Charlie, and kind of ad nauseum. This is totally fine. What really matters is, where does this process occur? If it happens on Alice's device, then you can safely say you're protecting her from attackers. Her privacy is not compromised. But of course, this is very unwieldy for a mainstream application. It would be like if you went onto Instagram and someone had put a new picture up, and you had to wait for them to come online to do this encryption on your behalf, which obviously wouldn't make sense. Which is why most applications will perform this operation on some remote server. Now, this has some problems. Of course, it's a honeypot of vulnerable data. As you can see, it's in plain text. So state actors or hackers, or indeed the data custodians themselves, are sort of given your trust. In a decentralized context, it's even worse. If you're using decentralized storage, instead of the re-encryption process occurring on some heavily protected data center operated by Dropbox or Google or whomever, it could kind of occur on the machine belonging to the adversary themselves. You don't really know. So I think if you're going to use a encrypted storage layer, you really need decentralized access control. Okay, I'm going to quickly explain how NewCipher addresses some of these problems, and then jump into the economic issues, which are many. Okay, so proxy encryption is the underlying cryptography. It starts with, in the same way as before, where the data owner encrypts some data with a public key and sends it off to a storage layer somewhere. Okay, and now there's an associated ciphertext. Let's not worry about that in detail. If Bob, the recipient, wanted to decrypt this ciphertext now and get access to the data, of course it won't work. It's only been encrypted for Alice. So in proxy re-encryption, what happens is her device generates a special key called a re-encryption key. She does this with her private key and Bob's, the recipient's, public key. This happens on her device, so her private key is not transferred anywhere, and it's very difficult to reconstruct her private key from the re-encryption key. In fact, you need collusion of all parties. this is a proxy. The proxy takes the re-encryption key, takes the ciphertext, and re-encrypts the ciphertext for Bob. I'm going to go into that a little bit more. And they do that in exchange for rewards and fees. And what emerges is a ciphertext for Bob and Bob only, and he can use this to access the data that Alice intended him to see. So this is a form of public key switching, but it has some unique advantages. One is that obviously you have a network of proxies, and so if Alice is offline, they can still perform the permission update. Secondly, you can attach any sort of arbitrary condition to access, so like only share with Bob if he pays. And of course, most importantly, unlike in the flow I showed you before, the data is encrypted end to end. Now, this is the interesting thing. We've decentralized proxy re-encryption. That's why it's threshold proxy re-encryption. The re-encryption key I mentioned before is actually split and sent out to many proxies. And each of them performs this individual re-encryption step. And then Bob will reconstruct the re-encryption key on his end, actually from a smaller number. It's an MFM scheme, and get that same ciphertext that allows him to get the data he deserves. Okay, and the point of that is that if you have a malicious or lazy or offline or incompetent proxy, then the power of the network, or like the fact that there are multiple proxies involved in a single sharing flow, ensures that the data reaches its destination. Okay, so now everybody is an expert in threshold proxy re-encryption. We can talk about the associated economic issues. As you might have guessed, the staker in our staking network is the proxy, or the node in the network. I'm going to use the term worker from now on, just to describe this generic work that's done. But the work is, well, one step of the work is re-encrypting as a proxy re-encryption node. In our code base, we also refer to them as Ursulas. I wish we had the consistency that I'm going to try and follow for the rest of this talk in our repo, but we don't. Okay, let's talk about the actual responsibilities of the worker. You can sort of break it down into three major areas. So one is the step you saw in the animation. When Bob issues a re-encryption request, the worker has to re-encrypt. And they also need to revoke access if Alice decides that. This is resting on the second responsibility, which is managing a sharing policy and also abiding by whatever rules or parameters are attached to it. And that sharing policy has an associated re-encryption key fragment, that little part of the re-encryption key, and they have to hold on to that. And this is actually quite important because unlike other resource networks, this means that the worker has to maintain a state on behalf of each customer or each user. So if in an outsourced computation network, you could sort of do the job and then everything resets, whereas in reality for a access control service, you might have a state that is persisting for 3, 6, 12 months or longer, in which you'll have access requests sent. And then the management, it sort of sits on top of availability. You could say this is like the most fundamental duty of a worker because it incurs the greatest overheads, actually being online. The other two don't really cost anything. They're extremely low overhead. And then within availability, you have the commitment to being online. This is the locking of tokens, the stake, and then actually being online at any given moment such that you're ready to answer a re-encryption request, a revocation, or a new sharing policy. Okay, I think this is an important starting point. These all look kind of familiar. Let's start with some like simple economic protocol building blocks. So you have to get tokens out to willing and capable service providers through a distribution. You need some action that's defined for a subsidy to be earned by a worker in lieu of a mature fee market. This is like to bootstrap the network, and therefore you have a basis for earning rewards. Then you have the payment channel, you have the fee structure, like what is the service unit that you're charging for, and you need to sample out nodes. In some networks, if that sampling is not done, or job assignment is not done with pure randomness, then it leads to conclusion issues. And then perhaps at the very bottom, the building block that is most distinctive from like a proof of work network is the fact you have slashing or some kind of punishment, some disincentive, and you need to decide like what are the violations that lead to some stake being deleted. There are some associated parameters that are very important too. So supply growth rate is obviously one that everybody knows about, like everyone talks about, like how fast is that supply growing, and therefore what is the effective yield for stakers. You also have interesting mechanisms that can sit on top of that, like adjusting the reward based on some post-launch activity. So you'll Live Peer speaking right after me, they have an interesting mechanism that aims for a healthy participation rate of 50% and changes the growth rate accordingly. Cosmos has a mechanism that is the second derivative of the growth rate. So it accelerates and decelerates the supply growth depending on how many people have bonded or staked. We have a reward coefficient, which is basically determined by how long you commit to, referring back to that commitment to being online. The minimum stake size is really a very important parameter because it's a trade-off between having something to lose and not setting a barrier that's sort of insurmountable and ending up with like a not very decentralized network. And then, of course, punishment calculation is really, really tricky as well. One thing to take into account, for example, with determining how you slash is like what is the repeatability of the offense. So to take a concrete example with NuCypher, imagine you had two workers, and both of them make exactly the same mistake, right? Let's say they screw up their implementation or the way that they run NuCypher software. But one has been assigned a sharing policy where the recipient is pinging them for re-encryption requests 1,000 times an hour because it's a vehicle that's communicating with other vehicles on the road. And the other one is pinging the worker B with a re-encryption request once a year because it's a patient sharing medical data with a doctor. If your punishment is per offense and the offense is tied to a re-encryption that's incorrect, then you're going to have one staker's collateral sort of being drained and the other one just gets a slap on the wrist even though they made the same mistake. So there's lots of complicated real-world factors that influence that too. And of course, these, the arbitration or verification process can incur third-party costs, like if you have some on-chain stuff. All right, I'm about to launch into a really complicated and kind of ugly diagram. So just try and memorize this, or at least memorize the notion that we have inputs and outputs, and some of them are measurable, and others exist but are not really measurable. They're just sort of discernible. I'll leave this in the corner. Okay, so along the top here, we have sort of the building blocks I just described, plus a couple others like the technical barrier to being a worker. That's quite important. So we have the grounds for punishment, the basis for earning rewards. Sorry for this big gap. You're going to see why there's a big gap in a second. I've added also some norms, which I think are a really interesting area of research as well, area of discussion. So you have a standard fee at the beginning. Of course, workers can change that, but it will anchor the users to a certain expectation on that service unit. So effective yield in the middle here, stake ratio or the participation rate, and the token value. I feel like these are the metrics that interested parties pay attention to the most at the moment. So they look at how much are they earning. If you're a staker in that, of course, you're thinking about that yield rate. By the way, yield is not a great term. It's sometimes called inflation, but let's just work with that for now. Of course, you're going to care about the revenue and the overheads and therefore your profit. But this is a very, very small part of the story, as you probably guessed. There are a whole host of other relevant outputs that a protocol designer needs to think about when designing their economic system. So I've kind of highlighted network adoption because from a product point of view, that's the most important, but it's not often talked about. You usually hear things like just the token value as this sort of proxy for the network success. Yes, this is very interdependent. Please don't try and understand this. Really, the only point I'm trying to make here is that there are a huge number of knock-on effects. Whenever you adjust one mechanism or one parameter, it has a broad impact across a range of different things. It affects the security, it affects the service availability, the prominence, the disincentive to misbehave, etc. And if you thought this wasn't going to get any worse, you're wrong. There's, of course, some fairly consistent alignment in terms of if you increase one metric the other one tends to go up. So for example, there's an interesting one. If the stake ratio or the participation rate goes up, that lowers the token liquidity, and that, by extension, can affect decentralization because there's less tokens for a would-be service provider to buy later after the network has launched. This is more like a cheat sheet when you're thinking about the whole system. Let's go into a couple problems. This is a really interesting one. This is an open problem, not one that we have a good solution for. There's a very big disconnect in service layer networks between subsidies or rewards or inflation or yield, whatever you want to call it, and the actual work that is done. And this, I think, is fairly distinctive, again, from a network where you're mining blocks, where you earn rewards based on the work you're doing. Of course, there are situations where you can mine empty blocks, etc. But in general, there's a much greater alignment between the subsidy and the actual work that the network is doing. In terms of how you bring these closer together, you have a couple options. So you can give rewards for being online. That's okay, but it's easy to fake a backend. And how often are you checking if somebody is online? What cost does that incur? Or you might be thinking, okay, well, why don't you give a reward for every time the kind of top layer work is done, which is performing a re-encryption? Well, of course, that's very vulnerable to Sybil attacks. You could just be sort of requesting work for yourself. And then you could say, okay, well, what if you limit that, or you put a cap on the earnable reward? That's sort of just a mitigation, not really solving it. So this is a really interesting problem to work on, and it's specific to the type of service that you're offering. Another interesting problem, I put these together because the solution we're working on addresses both, perhaps. So one is like, how do you monitor worker uptime, which is connected to the previous problem. And then you have a issue where, if your payouts are coming on-chain, then that's costing you gas. We're built on top of Ethereum. The solution we're looking at involves probabilistic micropayments and a sort of linked signature chain, where you are the probabilistic micropayments aspect, which Yondan might talk about because LivePeer does this, involves basically issuing tickets, and every so often one of those is redeemable, and so it sort of but it pays out more, and then if you have like enough throughput of the service and the payments, then it equals out. Okay, I'll talk about two more problems before I finish, where there's actually a solution that we've implemented. So starting right at the beginning, you need to get your stake out to these willing, capable service providers, and you want to optimize this for participation, for consolidation resistance, and for the network's overall reliability. NuCypher is fairly well known for this solution, which is called the work lock. I'm not going to go into detail here, but the basic idea is that as a would-be worker, instead of exchanging your ETH for new token, you lock it, you escrow it, and then you receive back some amount of new. And then when you do work in the network, that earns your right to unlock that ETH again. So the value of our token is actually derived from the opportunity cost of locking up the ETH, and we're creating another incentive layer for holders of the token to do work. Here's another enormous issue to which we only have a partial solution. How do you, if this service is decentralized and anyone can request from anyone else, how do you enforce the quality of the service and, by extension, the reliability and also the security? So we have a fairly interesting application of zero-knowledge proofs in order to ensure that when a worker re-encrypts, that the recipient can check that it's correct. So they haven't been manipulated by a different ciphertext. Remember, the output is a ciphertext, so it's not that easy to check. This is a quite sort of simplified flow, but essentially what happens is when the policy authority, or like the person controlling the data, Alice, issues out that first key fragment, it contains some metadata like a point commitment to the secret material in that key, and a few other things, like a few other signatures that sort of link it to her. The worker can check that everything is correct, that they all correspond. Then when Bob issues the access request, the worker doesn't just send the re-encryption, they also send a correctness proof. It's like a proof of knowledge. Bob can then check that. If it's invalid, then they send it to an adjudicator smart contract, which also can perform that check using some quite simple ECC arithmetic operations. And then if it's correct that the ciphertext and the proof don't correspond, then they can issue a penalty and delete some stake from the worker. I'll finish just by quickly putting a product hat on, something I think is not done enough in this space. Thinking about the world that this network inhabits and the influence that has on your protocol design. So key management systems, which are the closest sort of existing service to what the new Cypher network is offering, they charge usually per key and per decryption. Your ideal customer, your ideal user would have a very high throughput. And the reason for that is because the per re-encryption price, or the per decryption price, as it's called on Amazon KMS, for example, is very low. It's 3 cents for 10,000. But that also varies a lot by use case. So if you had, the example I used before was cars communicating with each other. If a car is driving down a motorway, it's going to be, a freeway, it's going to be communicating with lots of new cars. You're going to be creating lots of policies and issuing lots of requests. But again, if you use that patient-doctor relationship, you might just have one re-encryption request per year. This has a huge impact on how you design your economic system. And so it's important to think about. The unique selling points, so it's uncensorable, it's trustless, our network. It has some special capabilities like Alice can disappear. They're very difficult to price. The last two things I'll say is that, like many other projects in this space, since all of our code is open source, really the competitive advantage that NewCypher has are the collective, our workers as a whole, and how easy it is to migrate them over to another network, a competing network. That's sort of our major competitive advantage. And then as a corollary to that, these really important measures of how appealing or valuable our service is, the reliability, the ease of use, the cost effectiveness, they are also determined by the collective actions of the worker. And that, by extension, is determined by the effectiveness of your protocol design. So it's impossible to do product work in this space without thinking about the economic design. And I would say also, you shouldn't do economic design without thinking about sort of traditional product considerations. Thank you.
Probably have time for one question.
Hi, thank you very much. My question is very simple. What do you base your design decisions on?
So quite a few things. We started with doing some sort of empirical studies of existing networks. So if you were looking at something simple, like participation rate, we can look at, for example, how that compares to the historical effective yield, the historical token price as well. Again, that's a sort of measurable proxy for success. That's fairly new. Then more traditionally, if you're designing a slashing mechanism, then it's sort of correctness by design. It has to actually work. It's functional. It has maybe a few edge cases, but this is more like a cryptographic-led or security-led design decision. It depends what it is, really.